So our next speaker is Chen-Te Ma from Great Bay University. Please go ahead.
Okay, thank you. Thank you for the brief introduction. And also thank you for giving me this opportunity to present this research activity relating to ADS2, jetty gravity. Let me see whether I can. No, okay.
Hold it the other way around.
Hmm?
Turn it around.
It's flipped. It's flipped.
It's flipped.
Oh.
No? You're pointing towards you.
Yes.
The laser is in
Okay. Okay, thank you. Relating to the ADS2 jetty gravity SY model, and also we will explore this topic for the back reaction of the Dirac fermion matter by the quantum chaos and the quantum entanglement. My collaborator is Chris. He is from the Osaka University. Jeff is from Capital University, and Masaki from the Kyoto University. Let me first introduce the very simple model, jetty gravity, and also the boundary deal under the holographic millimeters SY model. Jetty gravity is the two-dimensional Dirac gravity theory, and which only has the linear coupling between the Dirac field and the Ricci scalar. So hence, it allows analytical solution to the boundary description and also the back reaction. And later I will introduce more about the back reaction. However, the jetty gravity is a model. This name of jetty gravity is named by Chen-Te Ma and Jackie. And this theory is boundary description is Schwarzschild theory at the low energy level and the larger limit. And this SY model is a quantum mechanics model, 0 plus 1 dimension. And this fermion field are the Majorana fermion field, and this J provides an O2O random O2O covering constant to each fermion field, and this J also follows the Gaussian distribution. And this N is a number of Majorana fermion. However, this model's large N and low energy limiter also provides a consistent boundary description to this effective theory. So hence we will say that the jetty gravity theory is due to SYK model under some holographic limit. And we are interested in the SYK model because it is solvable in the strong coupling limiter. Usually it's very hard to solve a model in the strong coupling limiter. So hence this model is very non-trivial. And this model also has a maximally chaotic in the sense of Yapon exponent, and also we can also see the carbon symmetry in the emergence limit, in some emergence limit like a large N. So hence we can use this model to understand quantum gravity of black hole, because this model has the graviton in the emergence limit. And we will and let me say that information products issue is a one important question that we need to understand. And to understand this issue, we should explore or develop the mechanism of the emergence. And we want to use this formula algebra to proceed this direction. A formula algebra is one general method to classify the operators in the Hilbert space. But however, we only can classify the bounded operator. But okay, let me first say the algebra first. The type 1 algebra is the algebra of all bounded operators, which correspond to the finite degrees of freedom. And then indeed, we usually think that this algebra can give a quantum gravity description, because all things are considered, and we have the whole degrees of freedom in this type 1 algebra. And then for type 2 algebra, we will lose a little. We lose the pure state. In this sense, we lose the states with the finite normalization. And we can also use the existence of the maximum limit state to distinguish the type 2-1 algebra from the type 2 infinity algebra. Usually we expect that this type 2 algebra corresponds to the semi-classical gravity. And for the type 3 case, it's a Backreaction algebra. We lose almost everything: pure state, density measure, and trace operation. For the clear sense, I want to define the trace operation first. The trace operation means that implies that the trace AB equals trace BA. If you see the trace AB does not equal to the trace BA, then it's not the trace operation here. Okay, but for the physical interpretation, this the gravity theory with the type 3 algebra should be the pure gravity. Okay, so it's our physical situation and the mathematical definition for this algebra. But however, when you in the quantum field theory or holographic theory, we usually meet the unbounded operator. So our approach is to first consider type 1 theory with a bounded operator, and then we take a large n or some hologram limit, and observe the physical observable, then see what algebra we get. To understand this approach, we first consider this extension of the SOIC model. This means that I introduce this equation 3, this 3 fermion term, with the conventional SOIC model. And this random common constant G has this equation 4 Gaussian distribution also. But now the G is a complex variable. And we want to study this model because this model's degree phase is always finite for each finite n case. So in this sense, we do not need to compute any physical observable by regularization. So it's more convenient to do this, to work the simulation to study this model. And in this model, the low energy distribution provide the backreaction of the Dirac fermion matter on the bulk. So, and due to our device of this n powers, so we can just see the large C limit, then we can see the pure gravity and this Dirac fermion matter simultaneously. So it's more easier to use a large n limiter to understand the backreaction here. But however, this model, equation 3, is a very weird model because this model does not, this term does not commute with the particle Hall operator. In instance, we lose some conventional symmetry here. But however, we speculate we will see the famous convention thing after we integrate out this random common constant G. Because after we integrate out this random common G, then we can see the 6th fermion term again. So we expect many familiar results will appear in the emergence limit. Later we will show this thing when we analyze the quantum chaos result. Okay. And first, let me first show our result for the summarize our result for the entangled entropy. Our simulation suggests that entangled entropy with a fixed initial state will have this result. But here we define the entangled entropy by the separation by partition between the Dirac fermion layer and the by the Majorana sector. So in this sense, our box theory by partition is between the Dirac fermion and the graviton. So now our entangled entropy result is that we first increase and then saturates to the maximally allowed value over n log 2 in the large n limit. And then we also find that the saturation time is finite in the large n limit. So in this sense, when we consider saturation region in the large n limit, the state is approximated by the maximum limit state. In this sense, if we consider this saturation region in the large n limit, we will see type 2-1 algebra. So hence, when we start from the finite n and then it approach to a large n limit, then we see the transition of algebra from the type 1 to a type 2-1. In this sense, we will say that the large n limiter loses information because when we go from the type 1 algebra to a type 2-1 algebra, we lose the pure state. So we lose some information from in the theory. And before we proceed to discuss show the result of the quantum chaos, we discuss the symmetry. the Hamiltonian or the three fermion term do not commute with these particle Hall operators. So hence we do this model is different from the conventional SYK model, and because it loses some conventional symmetry. But however, we still have some familiar symmetry, like because the Hamiltonian commutes with the charge conjugation operator. So hence we still have some conventional symmetry here. And then we find that we can just use this charge conjugation operator to provide the familiar the classification, and this classification is the same as the conventional SYK classification. We can still use the TD this number of the Dirac fermion to modulate 4 to see the 4 cases, and we can use which correspond to the P square, R square, or the charge conjugation operators to give this 4 cases classification. And this degeneracy in the spectrum is also same as the SYK model. And we also use the level spacing distribution to provide this Gaussian orthogonal ensemble, Gaussian unitary ensemble, and Gaussian symmetric ensembles. These 3 cases of classification. So hence, even if we do not have this particle Hall symmetry, the result of quantum chaos or the classification of quantum chaos, the result is very robust. So in this sense, we can only have this charge conjugation operator to get the conventional SYK quantum chaos result. Thank you for listening to my talk. Yeah.
We have time for a few questions.
So if I understand correctly, your model, then basically you have like 3 Dirac fermions coupled to some quantum dot, which is described by SYK, and then there is this Majorana coupling, this Yukawa coupling. So does this flow in the infrared to a boundary conformal field theory? And could you actually describe some of the phenomenology using boundary conformal field theory? Like a Kondo problem?
I do not know at this moment. Yes, yeah, I don't know, but I speculate because at the larger need you should see CFT. Yeah.
Well, it would be a BCFT in this case, but it could be interesting.
Yeah.
Any more?
I think you already asked the question I was going to ask, but can you, so this is, if I understand it correctly, it's SYK coupled to a CFT. And can you study like the evolution of entanglement in the CFT in the presence of the SYK model?
Of course, we can do it, but we did not we did not do that in this paper. Yeah, yeah. Of course, it's possible to do that.
Yeah.
Any others?